Hey, Gopal.
Hello.
So just confirming, the one-on-one meetings are still on, right?
Yeah, let me pull out your schedule.
Yeah, I'm at 1:30,
Okay.
according to the latest.
Yeah, they're on.
Great. So I'm just gonna put this, oh, I guess, I don't know if the schedule is public.
I think it's the doc is public.
Yeah, that. So this is it. Okay, great. So I'm going to listen to the talk, and then I'll look forward to talking to Varun. And thanks for organizing this.
Yeah, sure. No problem.
Hi, Gopal. Just to make sure, are you making the intro and hosting this talk?
Yeah.
Okay, sounds great.
Hi, Varun.
Hi, Gopal. How are you?
Good, good. Can we try sharing screens and see everything else?
Yeah,
properly?
sure. Oh, it says host disabled attendee screen sharing. Hi, Ina. Nice to see you.
Can you not share? Is there a problem?
You can try again. I think I just made it.
Yeah, no, it's working. Yeah.
Okay, perfect.
You can see the screen, right?
Yeah. Thanks.
Yeah.
And do you have any audio or video in the talk? If we might want to see the if the sound was.
I think there are some videos, but not audio. There is no audio.
Okay. Okay. Yeah. Yeah. That looks great.
So we'll wait for a couple of minutes and then we'll start the session.
Yeah, sounds good.
I think we can start now. I'm Gopal. I'm happy to have Dr. Varun Jampani from Google Research at Cambridge. Prior to that, he was a researcher at NVIDIA. He works in machine learning and computer vision, and his main interests include content adaptive neural networks, self-supervised visual discovery, and novel view synthesis. He obtained his PhD with honors from at MPI and University of Tübingen in Germany. He obtained his BTech and MS from IIIT Hyderabad in India, where he was a gold medalist. And his awesome work, SplatNet, has received the Best Paper Honorable Mention award at CVPR 2018. So yeah, Varun, stage is all yours now.
Yeah, thanks Gopal for the kind introduction. And yeah, I'm Varun from Google Research. Today I will be talking about our research works on this practical 3D object understanding from image collections and videos. So vision and objects go hand in hand in the sense that like significant part of computer vision is analyzing objects around us, because objects also play a central role in vision. Because objects give structure, like there's going to be seen as a meaningful groupings to the visual world. These visual groupings in turn help defining abstract concepts of objects, like what is a car. Like so we group things together to define an object. So vision and objects go hand in hand, and there are several significant part of computer vision problems such as detection, segmentation, or reconstruction involve analyzing objects around us. So much of the computer vision techniques have been focusing on, for the past few years, have been focusing on these supervised techniques, fully supervised techniques. So there are several challenges with these fully supervised techniques, is that like they cannot cover this long tail distribution of objects and categories. Suppose if we assume something about categories, known categories, and these things cannot work on like unknown category objects. And even actually within a new category, like these techniques often fail with outliers. For example, this canonical surface mapping work from CVPR 2020 that tries to map 3D model to 2D images, some correspondences. And so they assume a single humped camel model. So it fails to work when there is this two humped camel. So when we have some assumptions about a category, they usually tend to fail. Even within an object category, they tend to fail with the outliers. So the goal of this research direction is to automatically discover object properties from images and videos with very weak supervision, as weak as possible, with very weak assumptions about object category. By object properties, I mean it could be like this geometry properties like 3D shape, depth, viewpoint, and pose. Or it could be like appearance properties like material properties, like how the light is reflecting on the surfaces, like diffuse albedo, specular albedo, roughness, illumination. And also it could be like semantic properties like part segmentations, key points, and correspondences, semantic correspondences. So the key research question is that like how to estimate different of these object properties directly from image collections and videos, and how these different object properties can interact with each other, that can help each other in estimating these things. So videos and image collections provide rich constraints. So we will be using this self-supervised learning on videos and image collections. The set of constraints they provide include, like, for example, in videos, this optical flow provide very good correspondences across video frames for an object, where like how the object is moving. So we can actually tell a lot about the object from this optical flow itself. And the static background, so much of there is also a static background in the videos that allows for good camera estimation, how the camera is moving. So videos provide nice constraints that we can use even if we don't assume anything about priors on like which category the object is. So same with image collections. Suppose here I am showing these image collections of, let's say, when we type this CC130 Hercules in Google image search, we get these results. These are the top results. As you can see, there is like a lot of commonality across these objects in these images, they have this almost similar shape and like similar color and similar somewhat common material properties. So there is a lot of constraints that we can leverage across common between either images, image collections, or the common across video frames that we can leverage to learn about object properties. So image collections are also quite common, or not just videos. The image collections, I mean, it's a set of images with common object category of interest. And examples include image search results, photo collections, or tourist pictures of a landmark, etc. So general framework that people solve this problem in sense is use this analysis by synthesis framework. Like this, we usually design an analysis network that take images or video as input and produces these object properties. It could be like 3D shape materials or anything. And then we try to synthesize back these features or pixels using a synthesis network, or either this neural rendering or generative networks, so that we can actually close a loop, so that we can have a loss function with respect to given images. So this is a standard learning paradigm for self-supervised learning of object properties. But there are still several unanswered questions even within this paradigm, like this. Like what kind of analysis network that makes sense, well, what kind of synthesis network makes sense here, and what is a good object representation, and what are the additional self-supervised constraints that we can use. Usually just having this loop, this self-supervised constraint with respect to pixels or features is usually not enough. So what are the additional self-supervised constraints that we can use? So given this general, this is a general framework, and so I have been working on this problem with several students and colleagues with for the past few years. In CVPR 19, we have this work where given the image collections of objects, we can automatically discover object parts, like as shown here. And in another work, we have this, given the image collection of faces or some object, we can actually automatically discover the viewpoint, how the pose of the object is changing. And this is this work is not this is right side work on this too short shape and BRD. This is not completely self-supervised, but this is here actually we given the flash and no flash image without direct supervision on shape and without direct supervision on material properties, we're able to get some reasonable shape and material properties out. And this is follow-up work. This is a 3D shape discovery where we have these, like given the image collection of birds or cars or bikes, we are able to get some reasonable good reconstructions without assuming any direct supervision on these things. And we have a recent work where we also, in addition to 3D reconstruction, we also discover the corresponding 3D parts.
I believe in you, Cooper. You can do this. I don't know what exactly you're doing, but you got this.
I'm sorry, what's the question? Like,
yeah, I don't think it was a question. It was just,
okay.
Yeah, you can just carry on. Yeah.
Oh, okay, sounds good. Yeah. These. I just want to give a brief overview of these works, and in this talk, I will focus on more recent works. One is this neural reflectance decomposition. The aim is to estimate shape and materials from a given image collection. From this image collection of these, can we automatically get how to optimize for the shape and also the material properties like base color, roughness, so that we can actually use this in some graphics engines for rendering things. And in the later part of the talk, I will also discuss a couple of other works where the aim is given in video, can we how to get the articulated 3D shape, not just 3D shape, but how it is moving, this articulated 3D shape, just from a given video. Okay. So first I will talk about this work, this neural reflectance decomposition from image collections. So the aim is this to decompose the given the samples of given the sample images, these images from this unconstrained image collection. By unconstrained image collections, I mean like this. So each of these images are taken in different illumination conditions. And given the set of image collections, with this unconstrained illumination, can we optimize for this shape and material per image illumination and also material properties for this? So this will enable the relighting under any illumination. And also enables the view synthesis, like as shown in the result here. So there are actually two main challenges, like the rendering with BRDF and illumination is expensive. So if you want to use this differentiable rendering in this optimization pipeline, it is kind of expensive. And also the solution space is very highly ambiguous kind of thing, because estimating both shape and material properties, it's kind of like a very ambiguous problem. And also we need to estimate the illumination here. So we follow the similar optimization technique as NERF. Probably many of you might have been already familiar with this work. Like given these multi-view images, the aim here is to estimate some 3D shape, 3D neural volume, which encodes the radiance fields. So where the aim is to learn a multi-layer perceptron, which takes this XYZ location and also viewing direction as input, and also produces what is the color viewed along the direction. So these works got quite big success in last couple of years, last year, and they have been used in quite sorts of applications these days. And so we'll be following the similar strategy in our technique, where we learn a MLP that produces not only this densities, but also like explicit material properties. So NERF has several limitations, and NERF, because it does not, since there is no explicit decomposition of shape and material properties, there is no relighting. And also images needs to be captured in a single session, like it's the same illumination setting color. And also the inference time is quite long because we need to infer for the things. I think some of these limitations have been partially solved in the recent literature. I won't go into those details. So in this work, we try to address some of these limitations. So here in our work, we try to estimate this same like a neural volume given an image collection of objects taken from different illuminations. We want to estimate neural volume. Instead of encoding the radiance fields implicitly within this volume, we want to explicitly estimate like this density, like what is occupancy at that point, and also normals, diffuse albedo, specular albedo, and roughness. So we actually explicitly encode these material properties so that it enables us to get these explicit material properties out, as shown in figures here, like this diffuse albedo, specular albedo, roughness, and normals.
Varun, I have a quick question.
Yeah, sure.
So from in NERF, I understand that you need poses of these images, objects. So do you use structure promotion or something like that to acquire that?
Yeah, that's a good question. So yeah, I not clearly explain the inputs here. The inputs, yeah, there is a couple of inputs that we take from existing things. Like so in this work, we assume the poses are given. So we get the poses from Colmap in this work.
Okay.
And also we assume that segmentations are given for the object, since we don't know what is object, what is the background. So those are also assumed as given, like the segmentations of the objects are also assumed as given.
Yeah, makes sense.
So at each 3D point along the array, we estimate these base colors and metallic, roughness, and normals thing. And so in addition, since each image is taken from different illumination conditions, we also optimize per image illumination, enabling learning on images in the wild. So assuming you have the images taken by different people at different times of the day, let's say, assume that the people take the images of Statue of Liberty using different at different times. They have different illumination conditions. So using this technique, we can actually process those images as well, because we are learning illumination per image as well. So we use this physically based rendering instead of using NERF based implicit rendering. Like we along this ray we use physically based rendering using this BRDF parameters. these material properties, and as well as the spherical Gaussian illuminations. So we implemented a differentiable rendering that actually renders this, do some physically based rendering along the ray with BRDF and spherical Gaussians. And we also optimize the spherical Gaussian illuminations for a given image set kind of thing. So this is one example image on some synthetic data set. This is a ground truth environment map, and this is an optimized one from our these recovered spherical Gaussians from the NERD kind of thing. So in addition, what we also do is that like we explicitly another thing that we do in this work is that like we convert this implicit neural volume into explicit mesh. So where we first sample the points in a volume and then first create a point cloud, and then from this point cloud we remove the outliers, and then from that we create a mesh kind of thing. So this the nice thing with this is that like once we have this mesh with material properties, we can actually render in standard rendering engines. So comparison, this is one comparison with NERF where we can, the compared to NERF, we can handle varying illumination and also relight the objects. And NERF takes 30 seconds on a modern GPU to synthesize a novel view, whereas this NERD is capable of real-time inference after extraction because we have explicit mesh and with material properties. So these are some results on synthetic data sets. Given the images of these cars with different illumination conditions, we have these the extracted novel views and also in some novel environment map. And this is another result where we can see that we can also see some nice reflections on this steel-like surface, metallic surface. These are another result on synthetic chair, and this is one real-world example where the input is like image collections like this, and we have these related 3D model. So also in our web page we have results. Can you see this web page?
Yes.
Okay, yeah. So we also have some results on some real-world scenes where you can actually interactively render in this. Since we estimate explicit mesh and material properties, we can actually render also using browser renderers like where we use this Blender-based renderer, where you can actually put in different illumination conditions and visualize things. And we also tried this on like Statue of Liberty images downloaded from the internet. The results are not perfect because the Coal map does not give very exact poses, but it works reasonably okay. Like this is a reconstruction just from the in the wild images, and you can actually put this Statue of Liberty in different illumination conditions. And I will show you another example with this metallic surface. You can see more reflections and material properties. Like, for example, here is a synthetic globe scene where you can see this nice metallic surface reflections, and you can put in different environment maps to see the illumination changes here. So for the summary for this paper is that like we estimate shape and material properties from image collections, and image collections can be taken with varying illumination conditions. And we get explicit extraction of mesh with material properties. So in summary, we have these relatable 3D assets from image collections. So there are several limitations in this work. It requires foreground segmentation as well as camera poses, which we get from Coal map. And foreground segmentation, we manually draw these foreground segmentations. And it requires considerable number of input images. Right now, it requires around 100 images of an object. And also the spherical Gaussian illumination have several limitations, which we try to address in the next work. Yeah, so we have this follow-up work which we call neural pre-integrated lighting for reflector and decomposition. So there is this issue with spherical Gaussian illuminations, like because the spherical Gaussian is a very rough approximation. So if we add more spherical Gaussians, this, it can get more and more fidelity. We can get more and more fidelity, but the rendering time also gets also much slower. Still, the spherical Gaussians are very rough approximation for this. So before going to this technique, let's take a brief look into this rendering equation. In the rendering equation, this is a standard rendering equation which includes this integration of light with this over this entire hemisphere with this diffuse. This BD is a diffuse property, like diffuse property of the diffuse albedo, and this is this diffuse term and the specular term. This integration of the light over the hemisphere forms the center in these rendering equations, in this rendering process. So there are these existing works that actually, especially for example, even actually used in like this real-time shadings in Unreal Engine 4 or in some real-time rendering engines. The trick is that like they pre-integrate the light, and they integrate the light over different solid angles, and then they pre-store these pre-integrated illumination network, pre-integrated illuminations. For example, this is this illumination over these different solid angles, and using this different roughness. So they actually pre-store these pre-integrated illuminations, and then once we pre-store these pre-integrated illuminations, this rendering becomes simple matrix multiplications with these pre-integrated illuminations. So it is a bit involved. At a high level, you can think of for example, this is this environment map shown in 1D. So what this pre-integrated illumination does is that like it actually takes this angle along this environment map, and it also takes the roughness. As you actually increase the roughness, this pre-integrated illumination environment map becomes more and more blurry, kind of thing. So what these real-time rendering engines do is that like they pre-store these pre-integrated environment maps. They pre-compute these things so that the actual rendering becomes quite fast. Nothing. So this is still this light pre-integration is still expensive, since in our setting we are estimating illumination on the fly. So we cannot also do this pre-integrated illumination. It's still expensive. So on the fly, because we're also estimating illumination per image. So what we do is that like in this work, our key novelty is that like we propose a neural pill network that converts this light pre-integration into a simple network query. So we actually propose a new network architecture to represent light and also do the pre-integration at the same time. So this architecture of this network is this pill network is like this, like which takes this light embedding. We represent light with some embedding vector, and it also takes the direction as input, and it also takes the roughness. So this is kind of like we are actually trying to mimic this process, this light which takes this direction and roughness. In our case, it also takes the embedding, which represents the actual illumination itself. And we use this Pygan-based architecture, which actually modulates this linear layers. So this is an MLP that takes these three things as input and produces the integrated light directly. So once this is actually trained on some environment maps. So now once this is trained, this is actually frozen. So these kind of, you can think of this like a illumination network that actually takes some light embedding and roughness and direction and directly produces what is an integrated light at those locations. One nice properties with this compared to spherical Gaussians is that like this is actually much faster in terms of rendering process. And this is an example where given this sphere, we try to optimize the spherical Gaussians, and we also try to optimize these embeddings and roughness for these spheres. And this is actually the recovered illumination with spherical Gaussian optimization. As you can see, it is kind of quite blobby. And with this pill illumination, we can get much higher fidelity illumination kind of thing. So this is with different roughness levels. So we assume that the roughness is known. assuming the known roughness, we try to optimize these embeddings here, given this peer. And for this embedding, learned embedding, for this optimized embedding, we can get this illumination. And so probably I'll briefly skip this in the interest of time. So we also learned some smooth manifold autoencoders to actually learn some good embedding space for illumination and also for BRDFs. And these are some view synthesis results and relating results on the same setting. See, as I have shown in the previous NERD results. And this is the comparison with novel view synthesis using NERF, NERD, and this neural pill ours. So with NERF, we see some floaters. With the NERD, we see some blurry results, and with this neural pill, we get more higher fidelity results. So we get better results compared to all this, the previous work. And in summary for this second paper, it's mostly the aim is same. The estimate shape, BRDF, and illumination from images taken under different lightings. So we address two main challenges here. One is this expensive rendering with spherical Gaussians. We use this neural pill for fast and effective light integration. And we also have another novelty which I did not go into details, which is this smooth manifold autoencoders. So we get a state-of-the-art decomposition, view synthesis, and relating results compared to existing works. And there are still several limitations which we are trying to address in our current works, which is it requires foreground segmentation as well as camera poses, and it still requires considerable number of input images. It requires around 100 images to optimize these things. And yeah, so that's actually the first part of my talk. Any questions in the talk?
I have a quick question.
Yeah, sure.
So I think the high-level idea is kind of similar to NERF, where you're sort of overfitting one network on these collection of images. I'm wondering, did you try to have a generalization where you basically have an encoder which is pre-trained, and then you apply these things on novel shapes altogether?
Yeah, we did not go in that direction because here we explicitly want to be agnostic to categories. So we wanted to work on like any weird shapes that you can see the things. So we explicitly want this to be in more structure from motion setting where we want to be category agnostic and also shape agnostic. But yeah, what you're suggesting is probably makes a lot of sense if we actually go to low data regimes, if we have very few images to optimize. Let's say if you have only 3-4 images to optimize a shape, then we actually need to leverage priors on the shape as well. So at a high level in this works, we focus mostly on illumination priors and BRDF priors. In terms of shape priors, it would be good to actually leverage those encoder-based techniques. And yeah, that's also something we are thinking. We still don't have any, we still did not experiment in that direction.
Cool. Yeah, thank you.
So there is another set of works where we try to optimize the shape from videos, not from image collections. So the first work is this learning articulated shape reconstruction from a monocular video. And here the aim is given this monocular video, like with this, we also assume the segmentations are given for this object. What is a moving object? What is a moving object of interest? The aim is to estimate the reconstructed shape with articulation kind of thing. So these are this middle column shows our results, and this right column shows some existing template-based methods. So ours is template-free because we start with standard spear template. It can work on any type of object. And even the existing template-based techniques, they work well on things like humans, but they usually tend to fail getting these out of domain things like clothes here, or like this two-humped camel here. Nothing. So the compared to existing works, they are like if you actually draw the spectrum of things like from these template-based things, like assume these human templates, animal templates, or like dolphin templates, and if we assume like more and more free-form things, so they assume these templates very high quality templates, and there are some other works which assume some weak templates like very average shape, very weak templates, and they assume like some other works that assume skeletons. Here actually we aim to be very free form in the sense that like we assume only, we just start from a sphere and try to deform it to a any type of shape possible, kind of thing. So the key question is that like, can we recover an articulated shape from video without relying on template priors, without relying on any template thing. So this work, so we again choose this analysis by synthesis, where we try to optimize these different things given this video input, and we try to optimize these rest shape, bone transformations, skinning weights, and also camera, how this camera intrinsics and is a transforming. And we use a differentiable rendering to render the image back and to have the loss functions there. So I will explain each of these in a briefly in a bit more details. So to be actually more explicit, the input is these not just the video but also the segmentations and also the optical flow. We actually computed optical flow using some existing techniques. Here we use Raft, and then we actually using this differentiable rendering, we optimize these 4 states. Like one is this rest shape. Rest shape is nothing but like a base shape, which is parameterized as a deformation of a sphere. So we learn this vertex positions and colors. How this what is this? How to actually deform the sphere to get this shape. So this is rest shape. This is one thing that we're optimizing. Given the all video frames. And we actually model the articulations using these bones, like these, as you can see, these points in space, and with how they can be parameterized is these ellipsoids in space, and how they are moving with these 3D transformations, kind of thing. These are these bone transformations. So we actually randomly initialize these bones randomly in space, and then we just learn some transformations for each of these bones. Nothing. So they don't have any explicit meaning here, other than they should actually try to explain the given motions in an object.
Varun, I have a quick question.
Yeah.
So for the rest shape, is it like a canonical pose of whatever the object is, or?
Yeah. So the rest shape is in the canonical pose, and yeah. So the rest shape is in some canonical pose, like where in this work we also assume symmetry plane, left and right are somewhat symmetric. So the canonical pose is usually like between within that symmetric plane thing. So we use this estimated camera parameters to transform this canonical pose into the right pose.
Do you update the rest pose, I mean this canonical pose, over time, or is it kept constant from the frame 1?
So all of these are updated. All of these are like kind of learned, optimized. All of these are updated as the optimization progresses. There are some intermediate steps where we actually do some remeshing while optimizing. I will explain that a bit later.
Okay, cool. Thank you.
I think so all these things are optimized. So these are also randomly initialized and optimized jointly, and we also learn the skinning weights like this from this. So how these rest pose, how these mesh, these skinning weights, like how these mesh and bones are actually related to each other, like what is the weighting, like how much of each vertex in a mesh is influenced by a particular bone. Yeah, so those are the skinning weights. We also optimize the skinning weights, and we also learn this object camera transformations and also camera intrinsics. Nothing. So once we have this rest pose, bone transformations, and skinning weights, we can actually repose this object and also transform it based on these bone transformations. And then we also optimize the camera transformations and camera intrinsics, and we render 3 things with using soft rasterizer. Using Silhouettes, we render Silhouettes, we render texture, and we also render the optical flows. And we use loss functions with respect to these given silhouettes, given images, and given optical flow. And yeah, sorry, we did not use RAFT, but actually we use this VCN optical flow to get this optical flow, and also these annotations, or we use either manual annotations or point trend to get the segmentations. And we have these reconstruction loss functions with respect to estimated ones, and also the renderings and measurements, and this we optimize all of these 4 things with these reconstruction loss functions. And we also use several other constraints, like we assume the symmetry plane, and also assume that the symmetry shape and skinning weights are symmetric. And we also use these like as rigid as possible constraints, that the each of the object has to be as rigid as possible, and many things has to be explained by the motion articulation, and the temporal smoothness constraints, and also Laplacian regularization for the locally smoothness of the object shape. So another trick actually that actually made it work much better is this coarse to fine reconstruction. Initially, we start with like this coarse mesh reconstruction, and we get these reconstructions like this, and with actually no bones. This B indicates number of bones, M indicates number of vertices in a mesh, and then we do the remeshing with these higher resolution meshes, and we introduce more bones, and to get some higher resolution things, and then we repeat this multiple times to actually add more and more mesh vertices, and also add a bit more and more bones to actually get the richer and richer shapes just from videos. So these are some results. So this is the input video. This is PFU HD that assumes some kind of like human templates, and this is also Vibe, which assumes some kind of human template. And as you can see, we can actually get these details of clothes. Actually, PFU HD also get the details quite a bit, but it is kind of like a human specific kind of thing. Ours is category agnostic. And this is another one where this input video, this is this ACSM that use camel template. This is UMR, this unsupervised mesh reconstruction. They don't have a camel model. We use the horse model on this, and which fails. And with this laser, we can get much better articulations and reconstruction. And these are some results on Davis video results. As you can see, ours is a category agnostic, so we can also work with any whatever shape that is there. The results are not perfect, but it's very. This is one of the first works that showed that like just using image and optical flow, we can actually get quite good reconstruction. I mean, we get significantly much better results compared to existing works, especially on these deformable objects. So these are some of the results on this, like these are input videos and some other reconstructions. So in summary, for this laser work, we do this articulated shape reconstruction from monocular video without using any templates or category priors. And we have the comparable performance with model-based methods, and also applies to generic and unseen object categories. And it works quite reasonably well on unseen object categories. So we have this follow-up work where we fix some of the issues in this laser work, which we call VISEL, Video Surface Embeddings for Articulated 3D Shape Reconstruction. And these appeared in EURIPS 2021. And in the previous laser work, we only use optical flow that actually provide correspondences between adjacent frames. But actually, sometimes suppose if the object is moving quite a bit, it would be nice to have a long range correspondences to actually able to get better reconstructions kind of thing. So let's say if this person is moving, dancing, and here it would be nice to have these correspondences across these long-term video frames to actually get better reconstructions. So the way we do this is like we also learn, in addition to the things that we learn in laser, we also learn some surface embeddings that enables these long-range pixel correspondences as things. So specifically, we learn a CNN, 2D CNN that takes image as input and produces the features at each pixel location. And we also learn a 3D MLP that takes vertex location as input, vertex position as input, and also produces some features kind of thing. And then we do some kind of like embedding matching with these 3D embeddings and also these 2D embeddings. This way we can actually have a correspondence between every frame in a video via this 3D our 3D matching thing. So specifically we learn this surface encoder that takes 3D rest shape and takes the vertex locations as input and produces this embeddings FS. And it also takes image as input and produces the embeddings F file. And we do this embedding matching thing and to actually match embeddings to here by using some soft nearest neighbor kind of matching, this kind of differentiable matching. And we also use this differentiable rendering to actually render these surface properties, these surface features into things.
Varun, I have a question here. So the matching that you do, is it like densely done over the entire object?
Yeah, it is actually densely done. For each vertex, we find which of the pixels.
Okay,
match.
so I'm wondering is it possible to just do classical tracking to find correspondences, or is it not that good?
Yeah, actually, we tried tracking. They only give sparse correspondences, and they are not that robust as we wanted it to be, because we want to get dense reconstructions. So we want actually more dense tracking kind of thing. Okay. So that's why we try to optimize on our own, like optimize jointly this dense tracking as well.
Okay, cool.
So there are existing ones that use sparse tracks. They're okay, but they're not. But actually, we need more dense track for this. So that is actually briefly about the technique, and these are some of the results. And as you can see, this is the laser result, and this is the visor result. We get actually more details out from this, and also this is another result on the top where we get the compared to laser, we can get more details out of it because we have these dense tracks. So one of the nice things is that like we also get these nice dense tracks from a single video kind of thing, like nice dense tracking of the objects thing. And this is also showing this is actually the skinning weights also give some nice parts, kind of rough parts kind of thing. So this color coding is kind of like skinning weights. And so since we have these dense correspondences in this work, we also use same rest pose across different videos. So we can also have correspondences across videos, and we can actually combine different videos together and try to optimize. Even though each video has very small portion, we are able to get reasonable reconstructions from it, since we're able to combine multiple videos together. So summary here is that like we do this articulated 3D shape reconstruction from monocular videos. And the key technique is to learn long-range video correspondences with surface embeddings. And there are several interesting favorable properties. Is that like it is a template-free, category agnostic, and we get articulations. We also get parts, and in addition to laser, we also get these long-term trajectories and better results. So in summary, I have this. I talked about these two main directions, which we are still actively pursuing further to make them better. Like one is this neural reflectance decomposition from image collections, like just to give these image collections how to get these 3D shapes and material properties. And another direction is to estimate from videos how to get 3D shapes and articulations. In future, we also want to get these material properties from videos. And also we want to, from image collections, we also want to explore these non-rigid objects. So far, we are exploring only the rigid objects, and we want to explore the non-rigid objects and also articulation from image collections. So ideal goal is to estimate everything, the 3D object properties like shape, articulation, semantic properties, and the aim is to scale them to as much objects in the wild as possible. And so, yeah, we are currently working on several projects where we want to make this work more practical to work on any video or image collection in the wild. And yeah, that concludes my talk. And if you have any comments or suggestions, feel free to reach out. And also, if you're working on any related topic and looking for collaborations, feel free to reach out. Yeah, that kind of concludes my talk, actually.
Yeah, thanks, Varun, for this wonderful talk. And I think you summarized a lot of recent work really well. Thanks for that. Anyone has questions?
Can I ask a question? Oh, sorry.
Go ahead.
Yeah, sure.
I can ask it.
Yeah, I can ask after you. Yeah.
Okay, so I have one question. So there's a lot of work on non-rigid structure for motion, and I'm curious what happened to this algorithm. Like I've never seen good results from this kind of non-rigid structure for motion, but on rigid object, it seems like CoMap or other structure motion works well. What do you think? Like,
yeah, so yeah, I think you're right. Actually, we explored some existing non-rigid structure from motion. So the ones that work well, they only focus on like part of an object, like a back of a human or something like some cloth moving thing. They work on very specific settings. They're not. I think the key issue is that like having some nice correspondences across long-range objects, long-range motions is quite difficult. I think it's yeah, I think you're right also that the CoMap works quite well on the rigid objects scenarios. But somehow in this real world scenes in the wild settings, we also notice that like when the object is moving and articulating, CoMap fails to get reconstructions. I think the CoMap was quite well in getting object poses, but getting 3D shapes, it fails quite a bit.
I see. So you mean the bottleneck lies on the feature matching part for the non-rigid structure for motion?
Yeah, feature mapping, we need to get very good feature matches. And yeah, that's true.
Okay, thanks.
Yeah, I was curious about, so as I understand, like you said, like that you want to produce more like articulated shapes. And I thought my question is basically, so it seems that like your method currently has problem with us, like, you know, kind of smaller parts, and probably because like it optimizes kind of like to get the full shape right. And if the parts are smaller, it's kind of like neglecting them. Like legs, for example. And I thought my question is like basically, do you think maybe like disentangling of, like instead of using like one shape representation, maybe like representing shape as a combination of parts can help like to articulate?
Yeah, definitely. Actually, yeah, that's actually a very good point. Yeah, so this I see it as like these two works I see it as like an initial work. Like so far there has been no works that show that like we can actually achieve such quality results just from optical flow. But there are actually still a lot of issues like these. Yeah, it actually makes a lot of sense to actually use. I also like part representations quite a bit as an intermediate priors. It actually makes a lot of sense to actually make use of like part segmentations or part level reasoning to do this, because each part has usually simpler shapes. And yeah, I think parts are definitely useful to actually get more local reasoning compared to that. Here actually we had to use some hacks to do this remeshing and stuff. But with parts, I think it's more reasonable. Actually, we can enforce some stronger priors with parts. I definitely agree. But on the other hand, parts are again, it's also this dilemma with whatever prior we use. They may also, if we fall out of that prior, then it may not work well. For example, for clothes, it's difficult to 3D deforming things. It's difficult to model clothes. Yeah, ideally, probably we should combine parts as well as some implicit representations instead of mesh here to actually also get higher fidelity results. Here.
Thank you.
Anyone else?
I have another question. It's kind of
Yeah,
more
sure, go on.
technical kind of. I'm just kind of confused because maybe I'm confusing with it with the previous work later, but I think that you were deforming objects from a sphere, and in this like breakdance guy, I see that sometimes the shape has like different topology compared to sphere because it has like hole. Like when he.
Yeah, because actually we have this discrete step where we actually remesh kind of thing. So we start from sphere, but in the here we actually start from sphere, but after some time we actually remesh. Once we actually remesh, it can actually put some hole.
Then I have a related question. Is it a feature or a bug? It's because I'm asking because it's like if you start with a sphere, you basically kind of, if you like doing, I don't know, if it's a bug, sorry. So if you start with the sphere, you can't like in general get like something like, I don't know, like with different topology, which can be seen like as a kind of like downside of the method. But if this remeshing allows you to like, you know, get more complex topology than a sphere, then it's probably a feature.
Yeah, so again, there's this dilemma here, like how much strong prior. Actually, the sphere has a nice property that it actually enforces smoothness prior in geometry, like the objects would be locally smooth. On the other hand, it is restrictive because we cannot punch holes in it. And so this we see that kind of like a hacky way of punching holes as a discrete steps in between kind of thing. Ideally, we should like to this to be a continuous thing where we go from start from strong prior and then progressively add more and more details kind of thing. So it's kind of difficult to depends on the setting. It's difficult to say whether it's a feature or bug. It has both features and it also has both issues.
Thank you. Thank you.
Varun, I have a question. So I think in this entire talk that there is a lot going on in terms of learning representations. And so have you thought of how can we learn, or what kind of representations within, you know, self-supervision learning can you learn that could be helpful for these kind of tasks? So for example, if you are trying to generate shape using few images or just one image or a small video, I would imagine that a pre-trained network that has 3D priors could help. But it seems
they
like
definitely
big, and I'm not sure how to do it.
Yeah, you're talking about these 3D deep networks, or these deep networks that have these feature networks that can have a lot of strong priors, right? Like, so yeah, that's actually a good high-level question in the sense that like it's I'm always curious about like these different aspects, like this geometry and appearance. So far in this works I have shown, we are focusing mostly on these two aspects, geometry and appearance. And the semantic aspects, I feel these existing networks can help quite a bit, like this bottom-up semantic processing. Like the deep networks, existing deep networks are quite good in finding like what type of object it is, and like this recognizing object parts or recognizing the object itself, kind of like finding the localizing the key points. So I think in this low shot setting, this could be quite useful, and we are in the process of exploring the direction using these existing networks, the representations, how to make use of those in actually as a correspondences or like that as these mid-level priors. So far I haven't seen clear 2D networks that can actually reason about geometry and appearance. That I think there are these depth networks that works okay for scenes, but it's not clear if they're it's not clear. I think the existing deep networks, 2D deep networks, are more for the recognition tasks, and they seem to be learning more like textual properties rather than geometric properties. I'm not sure. Yeah, I might be wrong, but
yeah, I guess
does it answer your
it's
question?
definitely an open problem. Do
Yeah, sorry, go ahead. Yeah, sorry.
Do you have like what do you think the field should be looking at in terms of representations that these networks should learn? Because like the kind of representations that you want may inspire certain kind of self-supervision learning. So I'm wondering if you have thoughts on that.
Yeah, so ideally the network should also encode some kind of local geometric properties, right? Like the feature should also encode some local geometric properties. So for the encoding, it's mostly textural and some semantic properties to some extent. Let's say if we take some ImageNet trained networks or other these networks, it would be nice for them to also encode some local geometric properties, and but it is not clear how to do that exactly. Like it's.
Yeah, I mean, it's definitely a challenge without access to 3D learning all these representations.
Yeah. So on the other hand, it is also not clear if in enforcing geometric properties into these features, does it adversely affect the classification? Ideally, it should improve the classification, right? Like it.
Yeah, I mean, we could have specific representation learning for these kind of tasks, and we may not care about classification.
Yeah.
So I guess I have a related question here. Is do you think that there are limitation in terms of the data set that we have, or do you think there is a golden data set out there that you would want to make that could improve, that can help us in progressing in these kind of tasks?
Yeah, the dataset is one of the key limitations in terms of like right now we want to be self-supervised, as much self-supervised as possible. So I'm not too much worried about training, optimizing such models that I have presented today. I'm actually more worried about systematic evaluation of these techniques, right? Like once we let's say once we estimate some articulation and shape, we want to be able to estimate how good we are in terms of estimating the articulation, how good we are in terms of like estimating the shape, how good we are in terms of estimating the material properties and those stuff. So right now there are no direct benchmarks on this to systematically evaluate and progress. So we are actually using some proxy metrics like how well we are transferring the key points from one to another. Those are okay, but there are also ways to cheat those metrics, right? Cheat those evaluation metrics. I think in terms of evaluation, actually, datasets would play important role actually to actually make a good progress in this direction. Like even if not in terms of training, even if we have smaller data set, like probably hundreds of thousands of images or videos, even if not million, that would actually help quite a bit for these problems. Like, does that answer your question, or are you talking more about like?
Yeah, I think it answers my question. Okay, so I guess nobody else has questions. I can ask one more. Do you think in terms of synthetic environments are there in games, video games that we have? Do you think that those synthetic environments can be used to learn representations that can transfer to real kind of tasks? Have people tried it, or is it the gap between synthetic and real is too large?
Yeah, so I think the synthetic data sets is kind of like slightly difficult to obtain unless they are rigid objects. For rigid objects, I think they are quite useful. I think the synthetic data set, we are kind of indirectly enforcing our prior knowledge, because while creating synthetic data set, someone is actually manually designed those things, right? Because we know how these things move, and they manually enforce those movements there. And I think they help quite a bit, but my feeling is that like we hit bottleneck sooner there, in the sense that like we may probably have a fewer objects there, and it's difficult to get high quality synthetic data actually. So see.
Yeah, that makes sense.
So I think the synthetic data is definitely used. For example, in this, actually the NED work, we use synthetic data to learn priors on BRDFs and illuminations. So synthetic data is definitely useful for these physics properties, like how light reflects from a surface and how the surface should behave. So that is actually purely trained on synthetic data set, because it is impossible to get actually the real world data on these BRDF material properties. But on the other hand, at like high level 3D shape priors and how the objects are moving, I'm not sure how good the synthetic data will be.
Yeah, that makes sense. I guess, especially in non-rigid motion, in games, we have these priors of how humans move and so on. So we probably can't learn more than that.
Yeah.
Okay, yeah, thank you so much. I guess.
Cool. Yeah, sounds good. Is there a question or is this?
I guess we can conclude this session now. Thanks a lot, Varun, for this awesome talk and answering all our questions. I guess there is a break, and then there are a few one-on-one sessions.
Cool. Yeah, sounds good. Yeah. Thanks everyone for joining. Yeah.
Yeah.
Bye.
Bye.
Bye.